Anyone who is not familiar with Fable? So I assume you're familiar. So this is what we are going to use, and I will do actual coding. And if you wish, you can follow, or you can just interrupt me, or just watch, or just listen, whichever is convenient. And as I said, we the topic is. Can I just hide this thing? Yeah, let's just do that. Topic is road to Kleisli. Has anyone heard the term Kleisli? Anyone familiar with that? Heard it? Heard it? Maybe know it? A bit? Kinda? A bit? Okay. So what I'm going to talk about is actually probably you have seen, or maybe you have used almost. Probably, I give a chance if you do F# programming. It's very likely that you have already used, but it's a little bit attempt to formalize and just understand what's going on beneath, so that you get familiarized with that. So here there's this term called monads, and maybe this funny joke. Actually, it's not a joke. It's a real definition that monad is a monad in the category of endofunctors. So we'll talk about that. Generally, the tendency with F# programmers that they just try to avoid this concept of monad for not to confuse people. I'm no way a mathematician or a category theory specialist, but I'm just slightly, let's call it among friends, a bit familiar with how at least a portion of it applies to F# programming. So we'll just try to study how that works. I'll be using Fable, so that's a good thing. You can. It's a browser environment. I think I'll be able to proceed all my coding here. So I don't need a VS Code or kind of thing. And we'll start with well, you can just print a hello world. So if you're not familiar, this is the coding side. Fable is a F# transpiler. It can transpile F# code to JavaScript, Rust, Python, and TypeScript. In this case, we're going to generate JavaScript. And on the right bottom pane, you can see the output. So whenever I print something to console, then we will be able to see the output here. By the way, anytime you can feel free to interrupt me. We are among friends. Yeah, so let's start. Who has heard about this? Can anyone explain if you're familiar with that list.map? So this is a module and it has a function. Let me just grab the chat. Okay, that's a functor. True. What is a functor? Then I would ask. Yeah, that's correct. You're very well armed with the knowledge. A functor is a type that implements map and return. Okay, that's very good, I would say. And what is the implementation of map? So just because I implemented a function called map, does it make a functor automatically? Does anyone know? Well, it has to abide some laws, but the word functor comes from the func, which is a 16-year-old term from the functions root, which means to perform. A functor, well, it's a category theory term in a sense called performer, but it performs in a way that it actually does not change the structure of the thing. But we'll visit that. Let's just go a little bit more simple. So since we are familiar with that, we know that list.map for unfamiliar people, what it does is if we have a list like this kind of thing, right? Then list.map can just do some stuff with that. So I can just do this one, and then I can just print off stuff and print it out. So we can see the output. Cool. Since we covered the map, what does this do? Well, have you ever used this option.map? Yeah. So obviously, it won't work with yeah. It's a functor for option types, which is true. So in a sense, if we have someone, then we can do the same thing. X plus 1, right? And then we can print it off. And what it does is it's just lifting the function. We'll talk about it since you are already familiar with that. These are very basics, but actually, if you're familiar, but for people who are not familiar with that, they're not much basics. But we'll just discuss a little bit more, revisit this thing. Don't worry if you're not this for people who are watching the recording, if you're not familiar with that. And last question is, I'm pretty sure the attendees will know because they're very well armed already. What does this do? So for people who watch the recording, I'm just reading the meeting chat, and people are here very knowledgeable already. Yeah, it's slightly different. I think this was perhaps the most confusing part, the bind thing. But we'll revisit that. So let's start with a simple function. Let's start from the beginning. So this was just a rough warm up. Let's create a function called x and increment and x plus 1. Okay. And then what we're going to do is we are going to read some input. Obviously, because it's a browser environment, we can't read the input from like a console read line, but we'll implement our own version of read line. Okay. And we'll use some fable tricks here. I'm open the namespace called fable core. And JS native basically says that throw an exception. That's actually won't matter because we are going to tell Fable to actually utilize the browser API. So here I can write any JavaScript I want in its string, and then actually whenever Fable compiler sees read line, it will actually utilize that that item inside the string. I'm going to use the built-in prompt function that's baked in the browser. And that means whenever we invoke it, it will actually invoke the prompt function. And this requires to be string. Yeah, we need to give the type. So if I run this and if I hit 4, you can see at the right bottom, it's 4. Shall I zoom a bit or it is okay? Maybe one level zoom. Yeah, okay. So this is good. So we are able to read and write things. The next thing is let's just invent a function, validate, right? And then what validate is going to do is it will actually uh, check if this is an integer. And now, yeah, let's do that. So I'll just do try parse. Luckily, not only that works in .NET, but also works in Fable too. Basically, it returns a tuple, and if it's successfully parsed the given input, then I will just return the parsed value. Otherwise, I will just return none. Okay. This complains, if you look at this, says, well, I could not find the unique overload because the function also implements this span-based overload. So let's just make it clear that we are giving a string here to make it happy for a Fable specific environment. So we have a simple function that takes a string and then it actually converts to an integer if it can, and then returns a sum, right? Then we can actually try to get and read a number. Validate, right? We can get rid of these two lines now for the time being. And then, well, we can printf at the end. So let's try that, if that works. So if I hit a number, it returned 5. Okay, that's great. There's just a glitch with Fable REPL. Just need to reload. Okay. And if I enter a non-numeric value, it returns undefined. So we are actually emitting some of something or none. Why do we see a number and then undefined? Does anyone have an answer? So why do I see undefined? Why not none? So, okay, yeah, and yeah, that's true. Actually, in Fable documentation, it says null, so the documentation is slightly misleading. It actually, because in JavaScript there's something called null as well. It doesn't return null. But in .NET environment, does anyone know? Remember what happens? Regular .NET. It prints again null. Yeah. So in .NET environment, just because this is about avoiding allocation, that's the intention. Why null is chosen instead of none? Because returning an perhaps it could have been done as singleton object. I don't know. I suspect this is due to avoiding unnecessary allocation. But perhaps a singleton of none, could that be? Maybe for every type? I don't know. So that's the reason. And basically the sum is erased. And you do sum 5 in .NET, you would see sum of something really. But so if I run this with the integer, you will just see 4. So Fable just erases it, actually. That's a Fable specific thing. So don't be surprised why do I see 4 but not sum 4. Okay, cool. Now what we want is, we would like to apply this increment function to n. And this doesn't work. What can I do? Usually says, well, I'm expecting an int option, or I don't know, but given an int of int. That's a good solution. That's a good solution. We can update the increment function. Updating means refactoring it. Okay. What else? I think that's that. Mhm. Yeah. I wish what you said was true, because it is true in Haskell, but unfortunately, F sharp does not support higher kind of types. So at least kind of, I know, but we can't make a generic map. It doesn't work that way. It, but what you say is true. It's a F sharp limitation. It's what you say is true. Absolutely. There's nothing. Absolutely correct. Yeah. So let's just go simple. Let's just go simple. Uh, this already exists, but let's just re-implement that just to see how it works. So I'll just create another option module which will shadow the original functions if I define something like this, and then define a map function. Okay, and the map will be like, we'll get an f, then function sum x is equal to fx, sum fx, sorry. And if none, whatever, it will be none. Then we can simply, I'll explain what's going on here, but we can simply create a different function called, I'll call it lifted add, then option.map inc, oh, just so lifted inc, sorry. And then I can just replace here. And ta-da, our compilation issue is solved. So this is an implementation of map for option. And what it does is actually, it's not magical. The function keyword is actually the same as, if you're not familiar with that, what it does is it actually does this match x with. So we can write it this way or the other way. Not sure why it screws up, but yeah. So either that or that. It's the same thing. Essentially, we are matching the value, the incoming value, which will be the n here, right? And then, yeah, it's a sugar for pattern matching. Perhaps maybe .NET runtime compiles to a different thing. I'm not sure, because the function word is, I've seen sometimes it compiles a different binary, but I'm not sure how it works internally. But it's pattern matching. Basically, we are checking the x, and then it says that, well, if the x is a sum of x, then we extract the ingredient, we extract the value, apply the f, which is a regular function, and then wrap it again. If it is none, then there's nothing we can do. In a sense, which if you look at the signature of this map function, you will see something peculiar. That's actually what it does is if you have, let's just say, comment it out, A to B, then it generates, if you apply map here, it makes it, let's call it option A to option B. So as function programmers, we would like this kind of thing, because it allows us not to, while coding, we sometimes encounter this kind of types. It allows us to upgrade our functions without thinking much. So what Asad Beg was true, one way is just to go and alter this function, right, or create a new version. But it's far easier if I know how to apply map. I know that it converts both input and output to the values what I want. In this case, it will convert int to an option to option to int, which is, you can see the signature. It lifted both sides at the same time. Then that would work for me, right? Any objections or unclear parts? And by notion, this is actually called as functor. If something implements a map and perhaps a return, the return is just lifting. Let's just do that as well. I'll just call it lift, because this has, In Haskell, they call it pure. In F# they call return, sometimes written with return, something like that. People write it like that. Here I'll just call lift, and what it will be is just it's going to wrap the value. It's all about it. Lifting means taking something and upgrading to option. Okay, it's actually, if you notice, it's a structure preserving. These are both structure preserving options. So whatever I put inside, it's still there. I'm not altering anything. That's why it's structure preserving. So the thing is, for something to be a functor, it has to implement this map, and it also has to work in a structure preserving way. There's even formalization of it. The formalization says that a functor should have ID property and supports composition. So ID is something like this. If I have, let's call it something like ID2. So ID is a built-in F# function, right? It just gets a T and returns a T. If I apply a map, that should still preserve the ID-ness. That means still, it complains about the value restriction, but we can just mitigate that by, so if I just return something like sum 5 and printf %a, just complain. I thought it would have implied, oh no, sorry, it's the other way. Okay. So this actually does not change. So it's still an ID function, right? So one of the characteristics is option.map should also work properly with ID. And the second characteristic is, if I have a composition like FG, then if I do option map here, then this should be equal to option map F option map G. So whatever you write a functor, these are called functor laws. Okay. In other words, if your map function supports these two characteristics, then it's a functor. So if not, then it's not. So I've seen some cases people writing using fscheck to test these things, if it really, because fscheck is able to generate functions even if this conditions hold. Okay, but these are a bit theory. In a sense, a map is something that lives a function which has one input and one output. Any questions? Okay, cool. That means we can use option map for any function we like. That will just any function you hear, or any map, right? List.map, or if there is any, I'm not sure, the async.map, which don't exist, I presume. Yeah, but there are third-party libraries implement all of these things. The result.map, which also probably doesn't exist built. No, it exists actually. Yeah, I just remember. So you have to do this one by. Unfortunately, due to the F# nature, doesn't support higher kind of types. There is no built-in way to generalize this, but there are libraries like F# plus. You can check it out, which attempts to generalize it. Okay, cool. So what if our function is something like that? Sorry, x, y, x plus y. Now, let's just say we have that n1 is equal to read line, and we validate again. Okay, and let n2 is equal to read line, validate again. And then what we want is We want to add n1 and n2. Okay. It immediately complains that stating that, well, option doesn't support it because it's trying to infer it. We can help it out. That's just saying you're an integer. Okay. Now this one complains. Because they're option types, right? Not integers. What can we do about it? Can we kiss goodbye to our add function, or can we manipulate it just like we use map? Oh, lift it? How do we lift it? Okay, that's a good idea. Let's try. That's what I would do, to be fair. Okay, we have, and it doesn't complain. But let's look at the signature of lifted add. What do we see? We see that it's lifted the first thing, but then the inner part, so it's not exactly what we wanted, right? Let's just try to apply it. And it's happy, but ta-da, didn't work. Well, if you look at the signature, the second one, it expects an int. Yes, we can say sort of. So you can see the signature. It's still like, so the problem with map is actually map isn't the is intuitive to use it here, but unfortunately it's not the right thing, because map is a little bit more special case. It only works when your function has only one input. The add function has two input. So even with the help of partial application, still doesn't help. So for that, we need something else, which is called apply. So we need to invent another term. Okay, so let's do that. Apply, I'll call mf on mx, which denotes that lifted. So the m prefix denotes the lifted things. And magically, let's look at if I match these things. So we have a lifted function and lifted value, right? If both are lifted, and I'm going to extract them, extract the unlifted value and some effects. So I'll just, again, apply the inner values and then wrap it again. Otherwise, then it's just not. The apply, if you look at the signature, it takes something that is wrapped. Okay. So in other words, so we talked about lifted add equals the option dot lift add. Let's just lift the function first. So then we have this thing. Then if we apply the lifted add, okay. Now it actually what apply does is this. Sorry, I was completely confused for a while. I don't know why. If you have an option of A to B, okay, it returns option A to option B. So that's the magical part. This is what the apply does. Essentially, if you have the function itself is boxed into the value, okay, as in here. Let me just show it to you. As in here. So this one is just a function, well, with this three things, right? This is not with the two, but the three things. Let's just do that as well. So if you have this tree, then this would just do this. It essentially splits the first part. Am I making sense? So if you have a lifted value, it splits the first part. Then we end up with this part, right? Then we apply again. So here, if you take this part again, and we apply again, sorry, what will happen? Yes, correct. Then it will yield as option A, option B. So this is what we want, essentially. Okay. Option C. Let's do that if it works this way. Let's prove the case. So we already have the lifted value, so which means that we already have this one. Okay. The lifted add is option A, B, C, wrapped inside the box. Then what we do is we pass the lifted add to option apply. Okay. So this split it out. Now we are in this stage. Now we can pass the option A, which is N1, right? Just this way. There's a question. Is that the same as currying partial application? A part of it, yes. I mean, we are definitely doing currying, but we are also doing together with applying. Now, this part is so far is this one. Okay. This converted that part. Now, in addition, I just comment this star. It just doesn't work anyway. Then if I pass the n, then this means we apply this one. Then we are ended up with this part. Okay. Now this is the type. If we apply again, let's go part by part. If we apply again, now what will it be? It will be this. Now we can pass the n2. Just put this entire thing into parentheses, or just, and the result is option C. And we can print this out if you don't believe me. And I'll just comment all of these. Okay. Now, as a result, if I execute this thing, it should ask me two numbers, and it should just add them and then just return the result as long as they are both integers. So if I 4, okay, there's another one here. Let's just get rid of the first read line. Not to confuse us. Okay, let's do it again. 5, 3, you see 8. There's another printf here. Just also move it out. 5, y, then it's none, because we can't add 5 with none. Does this make sense? Let's just recap. what we did was we first lifted the entire function here, and that gave us a entire function wrapped. And I told you that the magic of apply is that once you have something like that, this can have any number of parameters. Doesn't matter. And then it actually detaches the first one. Since it is detached here, I can now pass the first parameter. Then I apply again, I detach the second part, and then I apply again. Well, this syntax looks awful, right? Now, from a Haskell standpoint of view, we say apply inherits, derives from map. That means apply actually can do everything that map can do. And you should agree, right? Because it's just, while map works for 2 parameters, I mean just one parameter only, one parameter input, apply works with any parameters. So it looks like the map is the functors, the special case, whereas apply is the officially called applicative functor, is actually a little bit more general. It actually supports any number of parameters. Okay, and I will make another one more claim. That is, map is actually equal to apply, return plus apply. So if you look at that, why this is true. If we have a function from A to B, if we return it, then it becomes, in the option case, prime A to prime B. Okay. And if we apply it, yes. If we apply it, then we have prime A to prime B. Is that clear? Why? This is actually a map, right? The whole operation, just we converted this thing to this thing. Then what we can, yeah? Yeah, apply separates, actually. This is the definition of apply. If you look at it here, it separates the first part. And this is what it did. It detached the first part. Okay. Then, in theory, we could do. So what we are going to do is, essentially, this is actually the same thing. Let's just invent a couple of operators just to make this, just to remedy this ugliness, right? So let's invent a couple of operators. Let's call this map. And this is not my invention. This is just a standard thing. And this is the apply. Okay. And I'll just do auto open so that I can use these operators. Okay. It's actually, it's a good question. How often do you use? So right, let me finish, because in this form, this is very, it looks very difficult to use because it looks very complex. Let's just tidy up, and then I'll try to answer your question. In a sense, I told you map is return plus apply, right? So lifted add is actually, if we go here, add, lift, apply, right? So can I, let's just copy this again. So I told you that this is true. If this is true, then I can just remove both of this, right? And write map here. Do you agree? If what I said is true, if return or lift, let's call it, lift plus apply is map, then I can just, instead of lift plus apply, I can just do you agree? Disagree? No opinion? Well, this is correct. You can do that. Okay. So let's just use that means actually we can just, now we have done this, we'll get rid of this parenthesis. Okay. Then instead of this, we can just do this. We can just use the operator. Because we said that the star is a map. Okay. We just take it back. So we were here. I just remove the parentheses. And then I just replace this with the operator, which is slightly easy to use. Okay. And then I can remove this parenthesis as well. Okay. Then remove this. Now here I can just use the apply. So this line and this line is identical. If I run it, so if I just pass a number, you can see it's 10 because it's the first printf comes from this line and the second printf comes from this line. If I pass, and it's none. So the question was, how often do you sell? As long as you need, but it's actually, once you invent these operators, using apply isn't very difficult. The first version looks very cumbersome, but in a sense, if you have a function with multiple inputs, then apply is the only way to lift it. Confusing? If you, for example, let's just add another parameter here. Our add, let's just say, not xy, but xyz. And let's just add this thing, right? 3 parameters. Then we can just do this. If we read it n3 here, and we can just do this n3. You can see it's very convenient actually. Super convenient. Now you ask me 3 numbers. Yeah, the first one's screwed up because the add function is no longer 2-parameter function. That's why the first one just actually returning a function. It's still expecting an input. But third, the later iteration works. Yes, so you don't have to. That means you can upgrade your functions without worrying about it. So the whole objective of all of these things is just you can reuse your existing functions. Just because I've written this kind of function and somehow like things like lifted values come, you don't have to go and write a newer version of your add thing. You can just reuse it. It's like a mechanical. You don't think, just upgrade it, apply, and that's done. Now let's come. Yeah, it is. It is. That's one of the appealing parts of function programming. Actually, so this takes a little bit time to grasp, but once you grasp it, it becomes very automatic. So you just code faster than the regular people who don't use these kind of things. It's powerful. Let's talk about the bind. Okay, so I'm pretty sure you're already one way or the other you're familiar with bind. But the scenario is this. Let's comment this out. So we have n1 already something that is an integer, right? And we want to, let's just say, validate it, but validate in the sense of, if this, for example, if it's greater than 0 or not. Okay, then it will be like something like if x is greater than 0, then some x, else none. So it's just we have this kind of function. Okay, so we have the n1, which is also already an integer, and this function also takes an integer, but it returns an option. So typically, validation functions returns an option. If you pass this validate for greater than, be able to work. Doesn't work, right? Why? It's a lifted value. It's yes, int option, right? So obviously this takes an int and you give an int option, it doesn't work. Okay, that's true. But what we want, the whole objective of this session is, yeah, yeah. So we were trying to somehow get away without unwrapping. We actually unwrap eventually. It's not something you can get away, but we're just encapsulating that thing. What we do is we create a function called bind, which is a very simple definition, actually. Then if you have some x, then just apply x. Otherwise, just return none. And that's the bind. The operator for this is designated as this one, but this is slightly tricky because it actually requires you to do the opposite of the thing because the nature of operator. And what to do is you bind mx. Okay, so this is the operator version of it. So we can use either of it. Let's try the operator version of it, and now it works. Yes, yes, as many as you want. So we can do 4, which prints 4. If we print x1, then it's undefined. You see, because it's lower than 0. That means you can do as much as you can, just as you stated. If you have many validators, you can just, well, okay, I screwed up. Because daytime I'm using Linux, and now I'm using Mac. I'm always messing up with the control key. Yeah, so you can see I can just add, but this could be a different validation. For example, the second validation can check if it is even. Right? 2 is equal to then sum, otherwise none. So then we can not only check for positiveness, but also the evenness. Then it means if I hit 6, it will work. If I hit 5, it will fail. And the good thing is it will short circuit. Actually, it's not going to. It will that once you have none, it will just propagate. Typically, in real programming, we don't use sum here. We use result types, result with error. So sometimes we want to propagate the error itself. And this also has two variants. One is the monadic variant, which is this version, and the other one is called applicative variant. So again, there was this question asked, do we use applicatives? Sometimes you want to accumulate all the errors, not just the first error, because if you use this current monadic version, your function will short circuit in the first error, and you will not be able to validate the subsequent ones. Okay, but the applicative version, which I'm not going to talk about it, is able to actually capture all the errors. Sometimes, and depends on what you want to do. Once we have so let's just talk about what bind does. Essentially, bind does this. If you have A and let's call it option, this could be anything, B, okay? Then bind gives you, and it converts it to option A to B. Essentially, it lifts the first part of it. That means it just lifts the input. That's what bind does. Is this clear? Yeah. So of course, it also has its own rules. Just I mean, any function lifting the first parameter does not make it a bind. It has its own rules, and this is what we are kind of talk about. So now this term comes. You heard this monad, right? So let's say that a monad is a monoid in the category of endofunctors. So what's an endofunctor? So we learned about the functor, but what's an endofunctor? Endofunctor is actually in F sharp. All functors are endofunctors because the category we are having here is the F sharp types. So whatever you do, you're always in F sharp scope. Okay. That means, well, from F sharp standpoint of view, we can just say, what's a category? It's a set of things with some arrows. An arrow represents an operation, that's like binding from one thing to another. Okay. Now let's just so it means we can say just briefly, we can roughly say a monad is a monoid of functors. And what is a monoid? Have you heard this term? All of you used it. I think all of you are familiar. A monoid is something that supports identity and associativity. That means if you have something like A times B, this is a regular multiplication, times C is equal to A times B times C, or you can use plus. So the multiplication along with, or addition along with the natural numbers, or just even the integers, the operation plus set of things makes it monoid. They also have both identity elements. For multiplication, the identity is 1, right? Times 1 is. So that's something you already know, a monoid. If you do multiplication with numbers, that's a monoid. It's just multiplication. If you do addition with integers, that's a monoid. So that's the definition of monoid, nothing else. That's all. Okay. If something has an identity element and it has associativity, then it's a monoid. Now, how does this apply to our thing? We require an identity. So what I claim is let mx is equal to sum of 5, okay? Or it could be a number. Then if I say a mix, so how we need a multiplication operator kind of thing. And that's where our bind will kick in. What I claim is for, let's just, for our monad, the identity operator element, not operator, is lift, okay? And let's just see that, if it's true. So I have this sum 5, and I claim if I multiply this by lift, then I end up with lift. So this should return true. The left-hand side is one part, and the right-hand side is the part. So you see that if this is really the identity operator, sorry, not operator, identity element, then what I should say is true. We can try. Let's just omit the previous read line, the printf. Just don't read. I don't need you. You can see it's true. Are you convinced that lift is our identity element? Okay. Okay, this is the easy part. What about the associativity, which is the more complex part? So let's define a function that is, let's just do this, something like a CVS. Our validate function, I'll just map it to an option, map it string. So this thing, if you remember, it was a string taking, and well, I can just use the validate maybe just instead of that. I'll just do that. So that will be less confusing. Our validate for 0, or they greater than 0. Okay, let's just use that. So what I claimed in mix again, okay, I'll just validate for even. Let's just validate for even. Doesn't matter. Okay. Then I validate for even again, or validate for greater than. Okay. So I have this value, and I multiply with this, then multiply with this. What I claim was, right? What did I claim? This one. Yeah. So the parenthesis, I'll just wrap the parenthesis here. This is associativity, right? So that means if I apply this right-hand part first, remember the definition of associativity. So if I multiply 3 by 5, then 7, that's still same with if I multiply 5 and 7 first, and then multiply with 3 later, doesn't change. So this is what I claim, which doesn't compile right now. But if I prove this, then that means we are yes. Yeah. If I prove this, this is a monoid. And it's a monoid of functor. It's like a functorial, well, so functorial structure a little bit more sharp standpoint of view, because a functor is also as actually a type that has this map. And I told you that apply inherits from functor and monads inherit from map. So all monads are also functors. Okay, but it's a special functor, so it's like a monoid kind of thing. But this doesn't compile, and we can make this compile with a little trick. I'll just slightly modify this thing. Okay, I'm not changing anything actually. What I did was, no, 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 there's no change here. No change. This was the original, and I just made a slight trick to make the compiler happy. I just convert this to an x and then pass the x. Okay, it's the same thing. I just acquire x and then pass the x. I don't make any change. See here? No, this won't compile, but this will compile, and this has no change. Okay. Then if I do printf, then this will also return true, and that proves, and that shows you why a monad, by definition, is a monoid in the category of functors, because it has the identity element, which is the return, and the bind is associative. Now, I'll just, maybe you're confused with this, but I'll convince you one more step, and that's where the Kleisli comes. Because Kleisli will make, the Kleisli is actually a functional composition for bind, so it's still bind, but it actually, so we use the Kleisli as this fishbone operator, which you're familiar with, giraffe and other things. And so it gets a lifted M and lifted G. And then what it does is I'll actually do the same thing. This is how you Kleisli. If I do MF and MG, okay. So once I have my fishbone operator defined, let's revisit this. Now maybe this you will be more convinced this time. Instead of, yeah, maybe, yeah. And now it's actually, it's just a helper kind of thing. What Kleisli does is, you're familiar with the regular composition operator, right? So it fuses two functions. So if you do FG, it fuses. But this requires F's output must match output type, must match the G's input type, right? In the case of Kleisli, let's call F being a function where x2 option prime A, more correctly, option A, option, let's call it B, okay? And G be prime B to option C. Just like F and G, the composition operator unifies F and G, the Kleisli operator is able to unify. That means F Kleisli fishbone, whatever you call, G is equal to, I mean, as a type, A prime A to option C. So it fuses just the same thing. That means you can combine any validation operator by using this, which is what I did. It's like a function composition over monadic functions. Hardcore. So maybe first time you see a bit, but actually if you see, it's just it's just sort of set of definitions. Some people decide that this is called this, and then yeah, absolutely. I'll share this file with you. It is the link, so you can check it out. The operator is taking MF and G, and then it says that, well, let's define an X and pass this X to MF, then bind it to MG. Why does it work this way? I can understand, but it's a little bit hard to explain. This part does nothing actually. It just allows the X to be so it introduces a variable to be forwarded through. Okay. Essentially, this composes, but without the help of it, if you remove this, it won't compile. Actually, this won't compile because it requires something to come in. Yeah. So I guess this is all I was going to share. So we went through all the way from functors to Kleisli. They are very practical concepts. In particular, for example, the Kleisli operator is used in Giraffe, or many Falco or this Onyx, these HTTP frameworks. That is because there's an input coming here, something like some HTTP request context, whatever. Okay, so every Giraffe handler, then you end up with something like a, well, Giraffe in the case of task of option of something, blah blah blah. So it just lifts it, and then what we like is the HTTP to be the pipeline to be composed, right? So you can in Giraffe you can compose pipelines like such as you do post, and you add a router here, right? Then you pass, for example, some sort of maybe authenticate. Then you pass your own handler here. Okay. So the request comes and then tries to pass through all these things, and at each step it can short circuit. It can say, well, this is not a post request, so it will short circuit. Then if it's a choice, so this is a Giraffe syntax, it will try the second one because this one is short circuited. Maybe it's a GET request, right? It will try. Maybe authentication failed here. Then depending on Giraffe, so Giraffe allows you to completely abort the request or just try the next one kind of thing. It can try the second one. But all of it boils down to this thing. It just, there's something lifted here. And then you want to compose many of them. Again, X, and then let's call it Y, for example, here. And this takes Y, lifted Y. And then there's lifted Z, for example. And then this goes to, it's about composition. It allows you to compose this function. You see that the left-hand side is not lifted. So it lifts it, and then you can just compose it. Lifted Q. Yes, I'll publish it to YouTube. You know, if you know my YouTube channel. If you don't, let me share the link. There are several videos there. Just find it. Just a second. Yeah, let me paste the link to the chat pane. So there are some videos, also you can watch other videos there. I'll post this thing to this entire thing, and let me share the link to this code pane. Here you can also actually also run the same code pane. Oh wait, it doesn't allow. Need a URL shortener. Just a second. Ah, shoot. URL shortener. Let me find the URL shortener. Yep, absolutely. That's a very good question. Oh, wait, none of the URL shortener. So what happens in F# community, because they're not, as just you say, they're not a part of the library. At some point, everyone attempted to do their own. Yeah, I shared a tiny URL. Everyone attempted their own library, and there is something called. So I think probably the most valid, most popular one, let's call it, not valid, is FS Toolkit. That implements all of these types. And let me share the link to you to that as well in the chat pane. And let me open here as well. So there's a NuGet package, and this thing implements, this library implements FS Toolkit, just most of the types. And then their respective, if you look at the option, if I expand, you can see the bind, map, map2, map3, traverse, which I haven't talked about it. Yeah, is available. Well, I don't see apply because the author opt in for map2. So yeah, that's a bit odd. I would have expected apply to be there. No, no. The challenge is that because F# doesn't support the higher kind of types by default, there might be a conflict. Yeah, but the other library, which probably a little more comprehensive, is the more hardcore library. Is called F# plops. So so yeah, I use F# toolkit by default, but not F# plus. F# plus is too powerful in the sense of it literally actually emulates higher kind of types, but it's too powerful. And sometimes if you have an error, it can return something very cryptic. It's somewhat it's not so easy to use, and I know how to use it, but still I avoid it also due to lack of Fable compatibility. Yes, map2 is apply, but it's for two inputs. So map3, and you can use map2, and you can say, well, I won't need 4 elements for inputs, then I won't need apply, which is an arguable. Yep, I guess this is all. Thank you for listening. If you want to reach me for any questions, I'm available on Twitter, probably, or from the Meetup channel. Bir şey değil. Yeah, thanks. Have a good day. Have a good weekend.